Okay, so the graph is going to look like it's going to start at positive A. And it's going to follow a motion like that, where this position down here is negative A. And what function is that? That's a cosine function. So this is the graph of simple harmonic motion. The position as a function of time is equal to A times the cosine of omega t. What would happen to this graph if omega stayed the same, everything stayed the same, but A changed? Yeah, just the height would change, but everything would happen at the same, the peaks would all happen at the same time value. And that has sort of a funny, kind of a surprising meaning for, like physically, for this system. What that says is, so let me write this down first. What if A increased, but omega stayed the same? So let me show you a graph here. Okay, so here's a cosine function for kind of an arbitrary value of omega. And the amplitude I chose was 0.1. So it goes from 0 to positive 0.1 and 0 to negative 0.1. So what's going to happen if I change this value to 0.5? You're going to see that we're still going to have 1, 2, 3, 4 peaks that happen at the same time values. Just the height changes. Okay. What that says is if you take this mass on a spring at rest and just give it the tiniest little nudge, okay, so it's moving just like a couple of millimeters, it's going to take the same amount of time to go through one oscillation, to go through each oscillation, as it will if you stretch the mass out half a meter and let it go. Okay, it's going to take the exact same amount of time for those two oscillations. That seems kind of impossible when you first think about it. First, it seems unlikely. And it'll always seem unlikely. That's how it comes out. But second, it seems impossible because when it's going through that tiny little motion, it's traveling such a small distance. And when it's going through, when you pull it out really far, it's going through such a big distance. How can it take the same amount of time? And the key to understanding that is just noticing that when you give it just a tiny little touch, it's moving really, really slowly, you know? And when you stretch it way out, it's moving really fast. The spring is jerking it back this way violently. And so you get this, even though when it has a big amplitude, it's going a long way, it's doing it really fast. And when it has a small amplitude, even though it's going a really small distance, it's doing it really slowly. And it turns out mathematically and experimentally, we'll see that it works, that those exactly offset each other and you get the same. And mathematically, that shows up as all of the peaks of these this cosine curve happening at the exact same times. Okay, they're just farther from the zero, from that resting position. Any questions about that? Okay, so what happens? So that's what happens if you change the amplitude. It doesn't have any effect on where the peaks occur. It only has an effect on how far from the resting position it is. What happens if you change the omega value? What happens if you increase the omega value? What do you think will happen to this curve? Yeah, it's going to smush it down. And if you make omega smaller, it's going to stretch it out. Okay? So I'm going to take this omega value and double it. And what you'll see is instead of 1, 2, 3, 4 peaks, you'll get twice as many, 8, maybe 9, because we have half of a peak there. But so I'm going to double this to 2, and you get more peaks. Did changing omega have any effect on the amplitude? Nope. And then you could go the opposite way, change this to 0.5. And you get fewer peaks. So if you increased A, but omega stayed the same, the peaks of the cosine curve occur at the same times, but they're greater. What if you increased omega, but the amplitude stayed the same? The pattern repeats more quickly. But the peaks are the same magnitude. Okay, so what affects A and omega physically? What are the things that affect those? So first, the amplitude. The only thing that affects the amplitude is pulling the mass farther from the resting length before you let it start oscillating. Okay? So if you pull the mass a different distance from the resting length, you get a different amplitude. Physically, what things in the system would you think might affect how quickly the pattern repeats? What? The spring constant is 1? Yep. And there's one other one. The mass, exactly. Those are the two things that affect it. So physically, if you increase the mass, I mentioned this, I know already, but if you increase the mass, it's harder for, without changing the spring, it's harder for that spring to change the directions to accelerate this bigger mass, right? And so it takes longer for it to turn it around this way, longer for it to turn it around over here. If without changing the mass, you increase the stiffness of the spring, then that spring is stronger and it's easier for it to pull that same mass, accelerate it this way, accelerate it that way. And so increasing the spring constant increases the omega, decreasing the spring constant, increasing the spring constant increases omega, increasing the mass decreases omega. Okay. So let's go into a little more detail with the angular frequency. So first, there's a formula for calculating it with a spring mass system. Omega is equal to the square root of k over m. And so, like I just said, increasing the spring constant causes an increase in the angular frequency. Increasing the mass causes a decrease in the angular frequency. And you can see mathematically that that works out. Also, angular frequency is equivalent to two other ways of expressing the same information. The first one is the period t. So I'll always write that as like a sort of a fancy capital T. The T is for time. And the period is the amount of time it takes for the cycle to repeat, for the pattern to repeat. The relationship between omega and the period is the period is equal to 2 pi over omega. So since you can calculate one directly from the other one, they have exactly the same information. You don't need to know any more than the angular frequency to get the period. You don't need to know any more than the period to get the angular frequency. You just use them in two different instances. Go back to this cosine graph for a second and let's draw the period on there. So if the period is the amount of time that it takes for the pattern to repeat itself, then go to two peaks like this. This amount of time is the period. So whenever you're trying to sketch a cosine graph that represents simple harmonic motion, knowing the period is more helpful than knowing omega, because that's where you draw the two peaks and then you can just sort of fill in the rest. The second way of representing the same information. Oh, I want to say one more thing before I go on. Notice that even though these have the same information in them, an increase in the period means a decrease in the angular frequency and vice versa. And that comes about because one is in the denominator in calculating the other one. Okay, so like if you double omega, it cuts t in half. Okay, so increasing the period is the same as decreasing the angular frequency and vice versa. And what are the SI units of the period? It's a measure of an amount of time, so this is just going to be in seconds. And the second way of representing this same information is the frequency. And the frequency is the number of cycles per unit time. You can calculate the frequency from the period as f is equal to 1 over the period. And so notice that increasing the period is equivalent to decreasing the frequency. And if you think about those definitions, it makes sense. Like, so if a motion is speeding up, then the amount of time for one cycle is getting smaller, right? It goes from 1/10 of a second for one cycle to a 1/100th of a second for one cycle. And what that means is you can fit more cycles into a single unit of time. So in 1 second, you go from 10 cycles in a second to 100 cycles in a second. And the SI units for frequency are 1 over seconds. And this is used often enough that it's given its own name, the hertz. And you abbreviate it as capital H, lowercase z. One thing to notice about the units is angular frequency, omega, also has SI units of 1 over seconds. But we won't call that hertz. And that's just so that we don't get confused about these two different variables that have two different meanings, even though they have the same units. Okay. It's the same thing last semester when we were talking about moments. Moments had the same units as energy, but we didn't use the units of joules for moments because those two things shouldn't be interchanged. Okay, any questions about that? Let me do one quick example of going back and forth between these. And so let's say that you were given a cosine graph like this, where this is negative 10, not negative, stupid idiot. That's positive 10, this is negative 10. This is position, time. And let's say that one period is, let's say, 2 seconds, okay? What's the function position as a function of time? Okay. So what are we going to have to do to use, well, we need to know two values in order to represent that position function. You know, we know it's going to be of the form a cosine of omega t. Okay. So we need to come up with the a, and we need to come up with the omega. A is the easier one to get. What's a looking at this graph? 10. But we're going to have to fiddle a little bit to come up with the omega value. How are we going to do that? Well, we're given this 2 seconds for the period, and we have an equation that relates the period to omega. So we'll just use that equation. So 2 seconds is equal to 2 pi over omega. And so omega is equal to pi. And now we can just plug these values in, and the position function is 10 times the cosine of pi t. If instead you were given this function and you were asked to sketch the curve, you would use this omega value to calculate the period, and then you'd know that one period apart are the two peaks of that graph, and then you'd fit the graph in there. Okay. Any questions about that? Okay, that's it. See you Thursday.